Hello, my name is Curtis Rendell, and I'm an ongoing master student for production and system development at the Technical University of Applied Science, Würzburg-Schweinfurt. I am also a research assistant for Professor Dr. Summer in his laboratory for quality, production measurement, and bearing technology. As working as a research assistant, Professor Dr. Summer assigned me and two other research assistants, Anna Heinle and Dominic Steffen, to analyze the impact of burnishing on the tribological properties of bearings, and in particular, the effect on tapered roller bearings. This is because he has the thesis that burnishing will reduce the surface roughness, and this will lead to an improvement in the tribological properties of the taper roller bearing due to the flaying fat contact that occurs in such a case. The way we designed our approach to analyze the effects of burnishing can be seen through our poster we created to publish our results. We divided the workload among the three of us. It was my job to gather the theoretical information on burnishing and then to develop a way to analyze the effects of this treatment to the surface it is applied on. Anna Heinle was then responsible for creating a suitable simulation model and then to simulate the results that have been gained through the analysis. To finish our research and to tie all loose ends, Dominic Steffen was then in charge of the practical tests so we could compare the measured and simulated data with the real life. So, if we look at what burnishing is, then we can see that this is a chemical reaction of an iron-rich material with a burnishing solution. This reaction is a redox reaction, where the iron gives the solution his electrons, undergoing an oxidation in which a very thin layer of mixed oxide consisting of FeO and Fe2O3 is developed, shown as in Figure 1. These are iron oxides, leading to the characteristic blackening of the surface, also shown in Figure 2 and 3. To mention here is that the exact ratio of FeO and Fe2O3 depends on the composition of the burnishing solution. Now let's look at the analysis of the surface. Important also to mention here is that we disassembled the bearings and measured the surface of each component multiple times before and after the treatment with the solution. The exact measuring location and direction is pictured in Figure 4, and the results of these measurements on the inner ring flank and the roller face are pictured in Figure 5 and 6. If we look at these graphs, we can see a significant decline of the surface roughness values of the inner ring flank and roller face after the treatment with the burnishing solution. These significant reductions all indicate that through this treatment, the tribological properties of the taper roller bearings must have been improved, and in particular because the reduction is also observed in the area where the flank face contact occurs. To verify these results, let's look at the simulation. For this, I will now let Anna Heinle take over.
Thank you, Curtis. My name is Anna Heinle, and I'm a bachelor student at the Technical University of Applied Science, Würzburg-Schweinfurt. And I'm also a research assistant in the laboratory of Professor Sommer. In this project, my main focus was on bearing simulation. For our simulation approach, I created a digital twin of a wheel hub in a bearing simulation program MESIS. This is what you can see here in the right upper corner. The aim of the simulation was to investigate the effects of burnishing on bearing lifespan and other important properties of bearings. So let's look at the results. In this diagram, for example, the bearing lifespan is plotted against temperature. At an oil temperature of 50 degrees Celsius, for instance, the lifespan of the burnished bearing is about 60% higher than the one of the bare bearing. Or regarding another point, at 70 degrees Celsius, the lifespan is still about 20% higher than the one of the untreated bearing. As you can see, the diagram shows clearly that a reduced surface roughness of the bearings through burnishing leads to a significant extension of the lifespan. Another great indicator for the advantages of burnishing is the viscosity ratio kappa. As shown in the diagram, the untreated bearing reaches the viscosity ratio of kappa equals 1 at 400 rounds per minute, while the burnished bearing achieves this ratio already at 180 rounds per minute. The viscosity ratio of kappa equals 2 is reached by the burnished bearing at 300 rounds per minute. The untreated bearing reaches this value significantly later at 900 rounds per minute. So you can see, the burnished bearing leaves the critical speed range significantly earlier. That leads to the formation of a fully separating lubricant film in an earlier stage. And this, in turn, reduces wear and increases the lifespan. Through these simulations, we confirmed that burnishing leads to significant improvements in the tribological properties of bearings. To further validate these results, we conducted also practical experiments, which will now be presented by my colleague Dominik Stephan.
Thank you, Anna, for your insightful overview of your simulation approach. My name is Dominik Stephan, and I'm a master student of product and system development, as well as a research assistant at the Technical University of Applied Science, Würzburg-Schweinfurt, and I am responsible for the practical tests. Now I like to shift gears and showcase the practical test results, highlighting the real-world application of our project. The test was conducted to validate the predictions of the theory and for the simulation. For this, we use an antimpariometer, which allows us to measure the tactile friction coefficient μ for both bare and burnished rollers and balls, following the specific test parameters shown here in figure 11. The acquired results shown in the diagram clarify the difference in friction behavior between the bare and burnished surfaces at different speeds. It needs to be highlighted that the burnished surface exhibits a higher boundary friction in very low speed ranges due to the soft-soft contact and a larger contact area resulting from the reduction of surface roughness. This behavior changes at 90 RPMs because the friction coefficient of the burnished component cuts the graph of the bare one, and from this date on, its value always remains below it. This indicates a faster transition to the mixed friction area. At higher speeds, the behavior is nearly identical. These friction tests demonstrate the effectiveness of surface burnishing, improving the tribological performances of turbo roller bearings. The transition from the mixed friction to the fluid friction occurs at a significantly lower speed range, RPMs. In summary, it can be concluded that the application of burnishing has positive effects of the treated surface. This is evident not only from surface measurements, but also from practical tests and simulations, which demonstrates a significant reduction in friction. If you have any questions about these topics, feel free to leave them in the comments below. For more information or if you're interested, please visit our YouTube channel.